Okay, so let's continue where we left off in the last class. Essentially, we were talking about constrained optimization and this idea of duality. All right, our goal is to solve an optimization problem of the following form. You want to minimize some function f of x subject to a bunch of inequality and equality constraints. Right, and the approach we took was the following. We defined the following quantity called the Lagrangian, which is a function of the variable x as well as some additional variables called the Lagrange multipliers, lambda and nu. So you have a Lagrange multiplier for each inequality constraint and each equality constraint. And we defined the Lagrange dual as the infimum of the Lagrangian over all x in the domain. Right? And the dual optimization problem was to maximize the Lagrange dual subject to the constraint that lambda is greater than or equal to 0. And we saw that if the following phenomena of strong duality holds, then the minimum value or the constrained minimum value for the primal optimization problem is equal to the solution to the dual optimization problem, right? In the value itself. But there's a more general framework wherein you can solve both the primal optimization problem and the dual optimization problem simultaneously by thinking about this optimization as, or the minimizer and maximizer, the two solutions together, as a saddle point for the Lagrangian. Right? So finding the saddle point of the Lagrangian can potentially give you the solutions to both the primal and the dual optimization problems if you have strong duality. Right? And you can have strong duality even without the problem being convex. You can have a non-convex problem where strong duality holds, and by finding the saddle point of the Lagrangian, you can solve both the primal and dual optimization problems simultaneously. And one way to do that is to solve for the KKT conditions. So we had a bunch of conditions, including primal feasibility, dual feasibility, stationarity, and complementary slackness. All right. So that's the gist of what we did in the last few classes. In today's class, and maybe a bit of the next class, we'll look at one specific application, and then maybe I'll spend a few classes talking about various algorithms that can be used to solve both unconstrained and constrained optimization problems. All right. So let me introduce a problem which some of you may have seen if you've taken the pattern recognition and machine learning course. If you've taken a basic machine learning course, then you would be familiar with this problem, but we'll look at it from an optimization perspective. The problem is linear classification. Right. So the problem is the following. You are given a bunch of points. You're given a bunch of points, x1, x2, up to let's say x capital N. These are all points in some Euclidean space, let's call it Rd. And each of these points has a label. The label is one of two. Either every point is labeled either 0 or 1. Yn. Right, so each yi is either 0 or 1. So I can maybe mark the points labeled 0 with an X and the points that are labeled 1 with a naught. Right? And at least in the context of this particular course, we'll view the linear classification problem in the following sense. Is it possible to separate out these two sets of points? And when I say linear classification, is it possible to draw a hyperplane that separates these two sets of points? All right. So this arises in the context of machine learning in a slightly different framework. The way you pose the problem is a little bit different, but we only want the most basic ideas that are required from machine learning. So the problem that we want to address is the following. Can we construct a hyperplane that separates the two sets? In this specific example, it turns out that we can. But it's not just enough to be able to construct a hyperplane, we also want to do it efficiently. With as low computational complexity as possible. And we want to pose this problem of constructing a hyperplane that separates these two sets of points as an optimization problem, so that we can use the tools of whatever optimization algorithms that we have at our disposal to solve this problem of linear classification. Okay, so let's see how we can solve this problem using optimization. So just for convenience, I'll split. So let's assume that this set is script x, the set of all possible points.
So is the problem to find whether there exists a plane or to find a plane itself?
Both.
If it is just finding whether a plane exists, we can directly invoke the separating hyperplane theorem, right? If there are two convex sets that are not overlapping, that is their intersection is 5, then we can definitely say that there exists a hyperplane. That is the theorem.
Correct.
So,
but then how do you do it efficiently?
how do we say two sets are convex, or like finding a set, whether a set is convex or not? It all depends on that algorithms.
Correct. Which is true, and we'll see the connection to what you just mentioned right now. But let's go there step by step. Okay. So let's say that x0 is the set of all points that are labeled 0, and x1 is the set of all points that are labeled 1. Zero. These are points labeled 1. All right, and x0. Okay. So what do we want? We want so there are two things. One is we want to know if there exists a solution, and if yes, we want to find at least one of those solutions. We want to find a hyperplane such that A transpose X or A transpose Xi is, let's say, greater than or equal to B, let's say greater than B, for all I in x0. I'll sort of interchangeably use xi and I to refer to the points labeled 0 versus those labeled 1. And A transpose xi is maybe less than or equal to B for all I that are labeled 1. Okay, so this is the linear classification problem, also called the linear discrimination problem. It's really more of a discrimination problem, but which arises out of the classification problem. Okay.
Are we limited to only one hyperplane? Can we have k hyperplanes?
There could be multiple hyperplanes. Maybe I don't.
If the points satisfy the conditions for two hyperplanes, then it's 0. Like you can have sort of polytope.
Oh, you mean that the discrimination could be that if it lies in this set defined by these hyperplanes, then it is labeled 0 or otherwise it is 1. Right? You could have different solutions, but we're going to look at the most basic version that we have. You just want to draw a hyperplane that separates the two, just one hyperplane. That is it. There are other ways. In fact, many of the techniques used for classification build on the ideas of linear classification, that is separation using hyperplanes. There are other techniques that you can use that build on the same algorithmic techniques. Effectively, suppose you, instead of separating these two sets using a hyperplane, maybe you want to separate them using a more complicated function. All right? For instance, it could be some other boundary. Right? It turns out to be possible using what are called kernel methods. It is possible to do non-linear classification using techniques that are, or by framing it as an optimization problem of linear classification, but in a different space. Okay. But anyway, that's a digression. So if you can solve this problem, in fact, you can solve a whole bunch of other problems as well. That's the point that I'm trying to make. So even the problem that you are talking about, wherein the separation of the two sets need not purely be using a hyperplane, but maybe something a lot more complicated, could be solved. It's easy to solve that if you can solve the following problem. So many solutions for those build on solutions to this simple looking problem. All right? Okay, is the problem clear? Great. So how do you frame this as an optimization problem in the standard form? Because after all, we want to the first thing we have to do is frame this optimization problem, or frame an optimization problem in this particular form. Because if we can do so, then we can use some other techniques to solve this. All right. Okay, what's the trouble with framing the optimization problem?
The function itself. This constraint would directly.
Yep. So it's clear what the constraint set should be, right? These are the constraints. You know what the constraints are, but what do you minimize, right? There's some function that you have to minimize.
You can't do like that.
Yeah.
Because you don't have anything to minimize, you can keep it as conveniently as possible. We can pick it to be convex, we can pick it to be very basic.
Really, but then that may not. I agree. So you could try to minimize any function you want subject to these constraints. But what's the simplest that you could do?
Like the volumetric type.
Misclassification, minimization misclassification.
You can do the sigma b minus a transpose xi minus b for I belongs to x.
Something a lot simpler. Why? So, okay, so let's see what we have so far. So we want to minimize something. Okay, something subject to the constraint, exactly
If you
these
sort of want to
constraints.
distance from the set of x0 sum and the set of x1 sum should be equal.
We'll get to that, but what's the most basic thing you could do? So in all of those, you're all saying some things, but in all of those, there are additional assumptions involved that you want to minimize this. We want to start with the simplest possible setting with no assumption whatsoever. As I said, I want to solve exactly this. I want to find one a comma b such that these conditions are satisfied.
What is the number of misclassifications?
So this is assuming that there is a misclassification, right? I want no misclassifications at all if possible. So what I want is that if there is a hyperplane that separates the two, then I want that hyperplane. If not, I want the algorithm to say, oh, there is no hyperplane that separates these two.
Minimize norm of A plus.
Again, you are making all of those assumptions. You just minimize a constant subject to these constraints. So if I'm able to solve this optimization problem, what would it give me?
The hyperplane.
It would give me a hyperplane that separates these two sets. All right. If not, if there is no point that satisfies these constraints, then it outputs nothing, right? Because there is no hyperplane that separates the two sets. Right. So this is the most basic version, and this is what is called a satisfiability problem, because you want to know if there is a point that satisfies the constraints. In fact, any satisfiability problem can be posed as a problem of minimizing a constant function subject to the constraints that you want to satisfy. Okay? But there is a problem with satisfiability, with most satisfiability problems, in that it's not efficiently it may or may not be efficiently solvable. And the reason is that there could be multiple solutions. In fact, there could be infinitely many solutions. Which solution do you look for? All right, there could be infinitely many hyperplanes that separate these two sets. If there's no hyperplane that separates the two sets, then fine, it doesn't matter. It's a 0 or 1 solution. But if there are multiple hyperplanes, which one do I prefer? Okay. Now that depends on the application at hand. It depends on what you define to be a good solution. At this point, we only want a solution. So one way of sort of improving the problem or improving the problem formulation is something what some of you suggested. So try to find that hyperplane for which the distance of the points to the hyperplane is as large as possible. So in a sense, to give a rough intuition, suppose that I have the following set of points. And I construct the following two hyperplanes. So this is one hyperplane that separates these two sets, and this is another hyperplane that separates the two sets. Which one would you prefer?
First one, purple.
The purple one is the one that you would prefer, right? It would be this one that you prefer over this one. There are reasons in the problem of when you study classification from a machine learning perspective, there are specific reasons why you prefer this classifier over this classifier. We'll not get into that as to there are deep reasons as to why you want to prefer the one. If you've taken the machine learning course, then in principle this would have a better generalization error than this particular classifier. But in any case, intuitively we see that this is better because this set only represents part of the information that you have about the two classes, and there is a lot more that you have not seen previously. So if you see an unseen sample, then it is more likely that this will have a better error performance than this one. Okay, because in some sense these two sets are better separated by the purple classifier compared to the blue classifier. Okay, so in words, what I could say is, now I can try to frame this optimization problem of finding the best linear classifier in some sense. But before I have a mathematical description, can you tell me what should be the objective function that I want to minimize or maximize?
You already put one, right?
Which?
You want to minimize one.
Correct, this is the one, but then this is also a solution to this particular problem, right? I want to get this solution and not this solution.
Maximize the
Okay,
distance.
maximize the distance. What distance?
Maximize the minimum distance of the distances to each of the circles, and then equate that.
Okay, so basically you try to find, for a given hyperplane that separates these two sets, I can try to find the distances, the minimum distance of each of these points from the hyperplane. So for each point and for every hyperplane, I get the minimum distance, or I find the distance and I find the minimum of all of these possible distances. So I want this minimum distance to be as large as possible. Okay, so let's introduce some terms. So given any xi, for a particular xi, a comma b, the margin of xi for a given classifier or for a given hyperplane is the distance from xi to the hyperplane. Okay, and among all of the i's, so I can try to find the minimum margin for among all of the points. I can try to find the minimum margin, and I want, so this is the margin for a given a comma b for a given hyperplane, and I want to choose that hyperplane for which this quantity, the minimum margin, is as large as possible. Okay, so I want to maximize the minimum margin. Of course, all of this is subject to the constraints that a comma b separates x0 and x1.
So can't we maximize the maximum point or the rightmost point of the left convex set and the
Can you speak up?
Can't we maximize the distance of the points from the boundary line?
Okay.
Points which are like the leftmost point of the convex cell, the rightmost point of that,
Uh-huh.
and of the right convex cell of the rightmost point.
Okay.
Right points and leftmost point of the right convex cell.
I think his doubt is mainly instead of doing it for all points, can you not find the boundary points and then minimize that distance?
Which boundary? You're talking about the boundary of the convex hull of x0 and x1.
Yeah.
Does it become any easier?
Assumption is that for boundary points there will be
Uh,
literally less than the total set.
Okay, but then that would require you to find which points define the convex hull of these two, right? That itself is an optimization problem. And in fact, we'll see that, we'll explore that in a little bit, okay? But this is our basic requirement. Right? If we can do this, then we are done. All right?
Can't you remove the constraint by adding the sign as well?
Which one?
Because the distance from x0 will be positive and distance from x1 will be negative.
Distance is always positive, right?
If you take A transpose xi minus b.
True. So I'm just trying to go step by step. Okay. We'll see that is what will happen. Okay. So what is the distance from xi to a comma b? Or the hyperplane defined by a comma b. So firstly, even before we proceed, does everybody agree with this particular formulation of the optimization problem? Or are there any questions? All right. So basically, the objective is the following. So for a given hyperplane, you have the margin. In this case, the minimum margin would be for the blue hyperplane. It would probably be the distance, this distance or this distance, one of those two. Whereas for the purple hyperplane, it would probably be this one. Okay, that would be the minimum margin. And among all possible hyperplanes that separate x0 and x1, we want to find the one that maximizes this minimum margin. Okay. So that's okay conceptually, but what is the minimum margin equal to, or what is the margin equal to? We've seen this previously, right? But now that we have sort of additional tools at our disposal, let's try to rederive what the minimum margin is, or what the margin is. Okay, so basically what we're given is we're given some point xi in Rd and we're given a comma b. We want to find the minimum distance, or we want to find the distance from xi to the hyperplane that is defined by a comma b. So the margin is equal to the distance from x to xi, or let me try to compute the square of the margin because it will be easier to find. The minimum over all x in the hyperplane, right? So you can think of the margin as the distance from xi to the closest point in the hyperplane. Right? So you're given this hyperplane, you are given some arbitrary point. The margin it's basically the perpendicular distance from this point xi to the hyperplane. But that's also equal to the distance from xi to the closest point in the hyperplane. So x such that A transpose x equal to B. Right? But then this is a constrained optimization problem now. Right? And we have some tools that we can use to solve constrained optimization problems. So let's try to solve it using Lagrange multipliers. Okay. So how would you go about? Let's define the Lagrangian. I have only one equality constraint, so I just need one Lagrange multiplier. This is equal to norm x minus xi square plus nu times A transpose x minus B. Okay. So firstly, what kind of an optimization problem is this? Okay, it's a quadratic problem. It's a quadratic minimization problem with a linear constraint. So it's a convex optimization problem. And does it satisfy Slater's condition? It trivially satisfies Slater's condition because there are no inequality constraints at all, right? So convex optimization problem that satisfies Slater's constraints, which means that I can just solve for this using KKT conditions, right? So what do the KKT conditions tell me? Firstly, the primal feasibility constraints. I have only one constraint, so I just want A transpose x to be equal to B, right? And I don't have any dual feasibility conditions, and I don't have any complementary slackness conditions. So I just need to set the gradient to be equal to 0. That's it, right? So the gradient of the Lagrangian with respect to x should be equal to 0. What is the gradient? Yes. So 2 times x minus xi times A, this should be equal to 0, right? Or x minus xi should be equal to half right. Now if I substitute this in the primal feasibility conditions, then I get A transpose, which one? Correct. This is a negative here. So if I substitute it back into the primal feasibility condition, then I get A transpose xi minus half mu times A. This should be equal to B, or ultimately I want to solve for nu, right? So just sort of rearranging, I get A transpose xi minus B should be equal to half mu A transpose A, which is norm A square, right? So nu is equal to 2 times A transpose xi minus b divided by norm A square. Now I can again my end goal is to find the objective function that minimizes this. If I put this back in x minus xi equal to minus half nu times a, then I basically get x minus xi should be equal to minus half of A transpose xi minus b times A divided by norm A squared. So the margin squared this is equal to norm of x minus xi the whole square. So maybe I should have been more careful here. This is x star you're right. There should be a 2. So the 2 and the half get cancelled. There's just a negative sign here. Right. So what will the square margin be equal to? This will be equal to norm A transpose xi minus b the whole square times norm A square divided by norm A square the whole square. So this is just this divided by norm A square, or the margin is equal to mod of A transpose xi minus b divided by norm A. Right? Question? And we sort of derived this using a slightly different approach towards the beginning of the course. Question? I'm sorry? Correct. X star minus xi is equal to this, correct? You take norm both sides and square it, correct? Which one? So this would be,
The denominator would be norm A power 4 and
yeah.
above it is norm A square.
So let's do that carefully. So norm x star minus xi square, this is equal to A transpose xi minus b divided by norm A square if I take the coefficient, the scalar coefficients outside, then I just get A transpose xi minus b the whole square divided by norm A to the power 4 times norm A square. The square and to the power 4 is the taker. Right? So the margin is just equal to A transpose mod of A transpose xi minus b divided by the 2 norm of A. All right. Okay. So basically what I want to do is I want to minimize the, maximize the minimum margin. So I'll frame the following, I'll write down the following optimization problem, and hopefully you'll agree with me that this is the same as what I had stated earlier. Let me call this a margin-based classifier. So let's say I want to maximize the margin. Let me call T the minimum margin. Okay. Subject to the constraint that A transpose xi minus b is greater than or equal to t for all I in x0, A transpose xi minus b is less than or equal to minus t for all I that are labeled 1, and t is greater than or equal to 0, but norm A is greater than or equal to 1. So let's suppose that we constrain the norm of A to be equal to 1. Okay, let me do that first. Norm of A equal to 1. Okay. In this case, what would be the margin? What would the margin be equal to? If the norm of A were equal to 1, then margin for xi, this would just be mod of A transpose xi minus b. You agree? Great. Now, what would that be for all of the points that are labeled 0? For all the points that are labeled 0, I have the condition that A transpose xi minus b should be greater than or equal to 0. Right, because that's how I'm defining the classifier. I have this additional constraint. So for all I in x0, I also want A transpose xi should be greater than or equal to b, which means that A transpose xi minus b is greater than or equal to 0. So the margin of xi is equal to A transpose xi minus b without the mod, because I know that that quantity is non-negative. Correct? And similarly, for all I in x1, the margin of xi, so A transpose xi is less than or equal to b, or whatever, A transpose. So A transpose xi minus b is negative. So the margin is in fact b minus A transpose xi. right? I want to ensure that the margin is at least t. Okay, to guarantee a margin that is at least t, I must make sure that A transpose xi minus b is greater than or equal to t for all points that are labeled 0, and A transpose and minus of A transpose xi minus b should be greater than or equal to t for all the points that are labeled 1. All right. So for all I in x0, I want margin to be at least t. So I want A transpose xi minus b should be greater than or equal to t. For all I that are labeled 1, I want A transpose xi minus b should be greater than or equal to t. Just rearranging those gives me these constraints. Okay, this is assuming that norm A is equal to 1. Okay, now I'm going to relax this condition by saying that norm A can be anything that is less than or equal to 1. Because as it will turn out, the complementary slackness condition will ensure that norm A should be equal to 1, because that particular Lagrange multiplier will not be allowed to be equal to 0. All right. But in any case, even if the norm of A is less than 1, if it is strictly less than 1, then the margin can actually only be larger. All right, because the margin is equal to A transpose xi minus b divided by norm of A. If norm of A is less than 1, then the margin is strictly larger than A transpose xi minus b. And I've demanded that these quantities are always greater than or equal to t, which will ensure that the margin is at least t, as long as norm of A is less than or equal to 1. All right. So that's how I end up with this particular optimization problem. Maximize t subject to the constraint that A transpose xi minus b is greater than or equal to t for all points labeled 0. A transpose xi minus b is less than or equal to minus t for all points labeled 1. I have this constraint that the margin should be non-negative and the norm of A should be less than or equal to 1.
So why is that even a constraint?
Which one?
Norm of A should be something.
If norm of A is greater than 1, then this is not equal to this is not a lower bound on the margin, right? So remember that the margin is equal to mod of A transpose xi minus b divided by the norm of A.
So what happens if norm of A is greater than 1?
If norm of A is greater than 1, then the margin is less than A transpose xi minus b. So all of my constraints are A transpose xi minus b is greater than or equal to t. So basically, if I
Aren't A and B relative sort of?
they are, but then I would have to change the objective function if I did not have this constraint.
You
So-
can have instead B equal to 1 as well, right?
Which one? D equal to 1?
B.
How?
Norm of A equal to.
How?
I mean, can't you like scale it as you wish?
No, right? So remember, for any A, B, this is what the margin is.
Yeah.
All right. Now, what I could have done is I could try to explicitly put this in the constraints. All right. But the only problem there would be that I would require A transpose xi minus b divided by the norm of A should be greater than or equal to t, and A transpose xi minus b divided by the norm of A should be less than or equal to minus t.
Yeah.
right? That's one way to do it. But the problem is then I have constraints that involve norm of A, like something divided by norm of A, which I could in principle rearrange, but as it will turn out, that's a more complicated optimization problem to solve. Because then I would have sort of product of two terms, two of the variables. Remember that A is a variable, it's an optimization variable. T is also an optimization variable. All right?
Can't you, you're sort of taking the normal vector, normal.
It's not unit norm, right? A is not guaranteed to be unit norm unless you impose that constraint.
Is there any, maybe I'll think again.
Sure, think about it, but another way of formulating would be you incorporate A in the objective function itself. But that will, you try to do it in any other way, you won't end up with a nice convex optimization problem. This, if you stare at it carefully, you see that this is a nice convex optimization problem. All right. If you try to involve the margin in any other way without invoking this specific constraint, then you will end up with something that's more complicated. All right. It's definitely you'll definitely get a valid optimization problem, but it may or may not be convex. All right. So these together, the first two constraints put together, ensure that mod A transpose xi minus b is greater than or equal to t, and the constraint that A transpose xi is greater than or equal to b right. That's what these two sets are equivalent. Okay, is this formulation okay?
So can you scroll to the
Yeah.
Changing the condition from norm of A equals to 1 to less than equal to 1 doesn't change the answer.
As it turns out, it doesn't change the answer. But in principle, the way if we formulated it, this should have been an equality constraint. All right. But then if I set norm of A equal to 1, then I end up with a non-convex optimization problem.
Why is it not convex?
What is the set of all points A such that norm of A is equal to 1? It's the surface of a sphere, all right, which is not a convex set. Because you take any 2 points on the surface of the sphere, the line joining the two does not lie on the surface anymore. Right? Okay, so I have this particular margin-based classifier. All right. So one thing is, okay, we can now go ahead and try to solve this. I'll reformulate this. Instead of maximizing t, I can minimize minus t, because it's so that it becomes a convex problem. So sorry, it's in the standard form. So minimize minus t subject to these particular constraints. So let me perhaps reformulate this in standard form. So I want to minimize minus t subject to the constraint that t minus A transpose xi plus b should be less than or equal to 0 for all I in x0, minus t minus A transpose xi plus b, I'm sorry, plus t plus A transpose xi minus b should be less than or equal to 0 for all should be less than or equal to 0 for all I in x1, minus t should be less than or equal to 0, and norm A minus 1 should be less than or equal to 0. Right, so that's my optimization problem in the standard form.
So does it checking for Slater's conditions like satisfy?
Sorry?
Checking for Slater's conditions.
Uh-huh.
Is it like satisfiable? How do you check for it?
How do you check for Slater's condition? So all you need to verify is there an A comma T which satisfies all of these constraints? A, B, and T that satisfies these constraints with strict inequality, right? And
That is satisfiability.
that is it's a little more than satisfiability. Let's try to see the geometric interpretation of Slater's condition. So suppose that this optimization problem satisfies Slater's condition, right? It would mean that there is some A and B such that, of course, norm of A is strictly less than 1, T is strictly greater than 0, and these are satisfied with strict inequality. So what is the geometric interpretation of that? Yeah, they are separable, and they are separable with a positive minimum margin, a strictly positive minimum margin. That is, I should be able to draw a hyperplane such that there are no points on this hyperplane. All of the points labeled 0 and 1 are strictly on the two opposite sides of the hyperplane. Right? As long as that happens, Slater's condition is satisfied.
But you can't verify.
Which one?
How do you check strong duality? You don't know how it is. Unless you're given.
Correct. So if they are so-called linearly separable, then Slater's condition is satisfied. And in fact, this will have a solution only if they are linearly separable. So all of this will work only if they're linearly separable. I can use a nice optimization. I can use the whole method of duality only if they're linearly separable. If not, then I can't. All right. So for now, let's assume that they're linearly separable, and then once we see what the solution looks like, let's then go ahead and try to see what happens if they are not linearly separable. Okay. So we'll assume that x0, x1 are linearly separable. Which means that there is at least one hyperplane that strictly separates these two sets. All right, and that's equivalent, if you think about it, to saying that the convex hulls of these of x0 and x1 are
Their intersection is 0.
non-intersecting. Right? All right. It requires a little bit of thought to show that they're equivalent. It's not just one implies the other, but they imply each other. Okay, so let's assume that they're linearly separable, and first let's try to construct the dual optimization problem. Okay, because that happens to have a nice geometric interpretation. What is the Lagrangian equal to? It's equal to minus t plus, so this will also require Lagrange multipliers. So I'll have a vector lambda 0 for the set of constraints, for the first set of constraints, a vector lambda 1 for the second set of constraints, and lambda 2 for minus t less than or equal to 0, and lambda 3 for norm a minus 1 less than or equal to 0. So this is minus t plus I in x0 lambda 0I times t minus A transpose xi minus b plus sum overall I in x1 lambda 1I times t plus A transpose xi minus b plus lambda 2 times minus t plus lambda 3 times norm a minus 1. Right? Okay, let me now to find the Lagrange dual function, I have to collect all of the terms involving a, involving b and t together. So let me do that. Let me first take all the terms that involve t. So it is t times minus 1 plus summation I in x0 of lambda 0I plus summation overall I in x1 lambda 1I. I don't have any other terms that, okay, the plus lambda 2 minus lambda 2. Right, so these are all the terms that multiples that t gets multiplied with, plus let's collect all of the terms that involve b. So b times summation I in x0 lambda 0I minus summation over all I in x1 of lambda 1I. None of the others involve b. Okay. Then I have all of the terms that involve a. So let's take A transpose. Let's look at those terms which are linear in A first. So this is A transpose times.
So can't you make it norm A square?
No, I don't want to. Right. That's a specific reason why I kept norm A and not norm A square. Okay, but that doesn't make it that much more complicated. All right. So A transpose, again, if I replace norm A with norm A square, the solution to my primal optimization problem doesn't change. But it does change the dual optimization problem. Right? I change A, I will get a different dual optimization problem. The primal solution does not change, but the dual optimization problem does change. So this is A transpose times minus sum overall I in x0 of lambda 0 I xi plus sum overall I in x1 lambda 1 I times xi. That's all that I have, plus whatever, lambda 3 times norm A minus lambda 3. Correct? Okay. So now I effectively have different terms. I have three sets of variables, A, B, and T. Right? And I need to take the infimum over A, B, and T. Correct? The nice thing is that there are no terms involving B and T, or B and A, or T and A. They're all nicely separated out. That's one of the reasons why I wanted this specific formulation. It becomes easy to construct the dual. Okay? So what is the infimum of this whole quantity with respect to T? Let's do it one variable. Let's try to think about it one variable at a time. So what happens to this whole, what is the infimum overall T? Yeah, infimum of this with respect to T.
You get the coefficient of T, whatever that thing
Mhm.
equal to 0. Right?
Sorry, can you rephrase what you just said?
So it differentiate with respect to T, partial differentiate, partial derivative, and then if you get
Again, when can you use that particular approach? You're trying to solve for the first order necessary conditions, but that works when
second order is always possible.
there's a lot more. There's an interior point which is a local minimum. All right. In this case, what kind of a function is it of T? It's a linear function of T. Right? Do you have an interior point that is a local minimum for a linear function?
The sign of it, and depending on that, you go to minus or plus infinity.
We're trying to minimize this over T. Right? And what are the conditions? Fine. We want to minimize this over all possible T. So what would the minimum be? What is the minimum of A times T? So what is the minimum of alpha times T? Minus infinity if alpha is non-zero. Right? So the Lagrange dual is equal to minus infinity if this is equal to 0, if this is non-zero. Likewise, it's also equal to minus infinity if this quantity is non-zero. Right? So the Lagrange dual is finite, can be finite, only if this coefficient is equal to 0 and this coefficient is equal to 0. Okay, that's number one. Right? That's observation number one. Now, okay, so now we know how to minimize with respect to B and T. What about A? In fact, a very similar question appeared in your exam, right?
The product should be negative, which means
The product
and
should
will
be
greater than 90.
okay. I mean, you got a question in a slightly different form. That is, you had to find the conjugate of something, right? Okay, I don't recall. It was there in the exam, right? The conjugate of norm of x. That question was there in the exam. Right? And what is the conjugate equal to? I mean, even if you don't remember, do you remember something about the conjugate?
Could be 0 and minus.
Yeah, it's equal to 0 or minus infinity, right? The conjugate of norm of x is either equal to 0 if some condition is satisfied, and it's equal to minus infinity if that condition is not satisfied. In fact,
Or normal y should be less than.
correct. So basically, suppose you have something of the following form. So you have infimum over all A in Rd of some alpha times norm of A plus some U transpose. So this is G of U transpose A. This is equal to minus infinity if norm of U is greater than alpha, and it's equal to 0 if norm of U is less than or equal to alpha. Okay, I think in the exam we basically had something of the form alpha, just norm of A plus U transpose A. All right. In this case, it's equal to minus infinity if norm of U is greater than 1. It's equal to 0 if the norm is less than or equal to 1.
Minus alpha.
I'm sorry?
Is it minus alpha?
So alpha is taken to be positive here, or non-negative, because you're minimizing with respect to A. In the conjugate, you are maximizing something minus norm of x with respect to A. Right. So all in all, the Lagrange dual function, this is equal to, so essentially,
It should be minus alpha. Right?
which one? You're minimizing with respect to it, right? Okay. So essentially, if this quantity is non-zero, or this quantity is non-zero, or if lambda 3 is greater than something, or if this quantity, the norm of this quantity is greater than something, then the Lagrange dual is equal to minus infinity. If not, so what is the finite value it can take? The first term would be equal to 0. The second term would also be equal to 0. This term would also be equal to 0. Right? So then all that, if it is finite, then this would be just minus lambda 3. All right? So it's finite if the quantity, if this term is equal to 0, or these two are equal to 1 plus lambda 2. Right, so it's if summation I in x0 lambda 0 I plus summation I in x1 lambda 1 I is equal to 1 plus lambda 2. And this quantity has to be equal to 0, which means that summation overall I in x0 of lambda 0 I should be equal to summation overall I in x1 of lambda 1 I. Okay, and so let's look at this particular quantity. It should be the case that the norm of this particular quantity should be less than or equal to lambda 3. Norm of summation I in x0 lambda 0 I xi minus summation I in x1 lambda 1 I xi should be less than or equal to lambda 3. If not, if any of these conditions are not satisfied, then it's equal to minus infinity.
So this is the last condition. Reduce.
Which one?
The less than lambda,
Why?
because the above condition
Which above condition?
equal to
No. So this only says that these coefficients should be equal to each other. Here you have the xi's. Remember that these are vectors, right? Okay, so now let's sort of try to interpret these conditions geometrically. Okay, what does this look like, or this look like? It looks like it's basically a non-negative linear combination. It may not exactly be convex, but yeah, it could be any affine. It's in fact any conic combination. Could be in general any conic combination. But if I combine with these, what do I get? So remember that the sum of the lambda 0 i's should be equal to the sum of the lambda 1 i's. And the sum of the lambda 0 i's and the sum of the lambda 1 i's put together, they should be 1 plus lambda 2.
Each one should be 1 plus lambda divided 2.
Correct. So basically each one should be equal to, this should be equal to 1 plus lambda 2 whole divided by 2. So effectively I can sort of rescale things up a little bit. If I rescale things, then this I can interpret. So remember that, right? So lambda 0 I. So this quantity, I can say that this should be less than or equal to lambda 3, or if I sort of try to normalize this, if I sort of divide this by 1 plus lambda 2 by 2, 1 plus lambda 2 by 2, by 2, then this quantity is nothing but a convex combination of the xi's of points labeled 0. This is a convex combination of xi's for points labeled 1, right? and this is less. This has to be less than or equal to lambda 3. And I want to minimize minus lambda 3 or I want to maximize minus lambda 3 or minimize lambda 3. Which is, what does this tell us? So effectively, what does a point here correspond to?
Point inside.
It corresponds to a point in the convex hull of the points labeled 0. This is a point in the convex hull of the points labeled 1. So effectively, if you think about it a little carefully, what this optimization problem tries to find out is what is the distance between the convex hulls of the points labeled 0 and the convex hull of the points labeled 1. Right? So effectively, the geometric interpretation of the dual is that you have the convex hull of all the points that are labeled 0. You have the convex hull of all points that are labeled 1. The minimum distance between these two convex hulls, right? Because I have a maximization of lambda 3, which effectively corresponds to a minimization of plus lambda 3. And the solution to this is a scaled version, maybe. But yeah, I mean, all of the rescaling, in the end, it will turn out that this is just the minimum distance between, or I think half of the minimum distance between these two convex hulls. Because after all, what we are trying to do is trying to maximize the minimum margin. So geometrically, the solution that you end up with, that will correspond to a hyperplane that passes through exactly the midpoint of the shortest distance or the line that joins the two closest points in the convex hulls. All right. In fact, this will be perpendicular to this particular line that separates the two convex hulls. So this tells you something about the solution which you kind of expected, right? Intuitively, you would expect that is the case. And this tells you just by looking at the dual, by interpreting the dual geometrically, that's exactly what you get. All right? Okay, any questions? It should be perpendicular, but yes, that's true. Well, in the end, I mean, that is still sort of geometric, but what the dual gives you is only the distance between the convex hulls. It doesn't tell you anything about the hyperplane itself, because the hyperplane is not part of the dual optimization problem. Because the hyperplane was part of the primal optimization problem.
So this actually might not be the optimal hyperplane.
That ends up being the optimal hyperplane, but that's not something you can conclude just by looking at the dual.
No, but Slater's condition is satisfied, so T star equals P star, right? So this has to be.
Correct, but just the dual optimization problem cannot tell you anything about the hyperplane, because the hyperplane is not, the variables for the dual optimization problem do not involve the hyperplane at all. All right. Okay, so let's.
That point in the convex hull of 0 always one of the x's.
Need not be. Why? Again, maybe let me try to draw a picture. Suppose I have something of the following form. So this is the convex hull of x0, but this is the convex hull of x1. So this is the minimum distance, right? This point is not a vertex.
Essentially, in this class, we try to get a very close form expression.
We didn't get a fully closed form expression, right? Yeah, just one.